Hi everyone, I'm Daniil, this is Anna, and today we are presenting our study on data splitting strategies for sequential recommenders. As we know, sequential recommenders dominate next item prediction task in both academia and industry. However, evaluation protocols are lagging behind. The leave and out split was used in many fundamental studies and still remains the most popular approach. This split is simple. It matches next item prediction, but it breaks the global timeline, causing temporal leakage and unrealistically long test horizon. A known alternative is a global temporal split. We train on the past and evaluate strictly using future data. This eliminates leakage and gives us control over the test period duration. However, global temporal split alone misaligns the next item prediction as it treats all post-cutoff items at once as targets. We reviewed previous works to identify viable alternatives of the papers published in the past 3 years. The majority used leave and out based splits or global temporal splits, and actually only a small percent used and combined GTS with next item prediction. So realistic leakage-free setups remain rare. We also checked popular frameworks, and again, most of them implement leave and out and global temporal splits, but they do not provide their combinations out of the box, which slows the adoption of rich evaluation strategies. To align GTS with next item prediction, we define the target inside the holdout part of a sequence for each test user. Instead of using a widespread all items target, as we discussed, it's not tailored for our task, we can consider the more task-aligned targets. For each test user, we can take either first, last, random, or successive targets. Now let's take a closer look at the successive evaluation scheme. It uses each future interaction as a separate target while incrementally extending the user history. This mirrors actually real model usage in an inline scenario and estimates an average post-cutoff performance. As a result, for n holdout interactions, we obtain n separate metric evaluations, cheaply enhancing robustness and capturing change in user behavior. So we performed extensive experiments across 6 splits and targets, 8 datasets, and 4 models to address the following research questions. The last 2 can be found actually in the paper. Here we will cover the first 4.
And the first one is what are statistical properties of subsets obtaining with different splitting strategies? And the first important property is the number of test users. Global temporal split reduces the number of test users compared to the leave and out split, and it could affect robustness of evaluation results. The other important property is the duration of test period. We observed that the test period for leave and out split is unrealistically long. It is more than 65% of the full dataset duration, and it overlaps with the training period. In contrast, global temporal split allows us to bound and align the test period duration with the real-world model usage. So, selecting a splitting strategy, we face a trade-off between the number of test users, volume of training data, and duration of test period. When using a global temporal split, we must choose a dataset-specific quantile or test window and check and report the splitting results. Let's move to the next research question. If the targets are equal in terms of temporal properties of interactions, we compared time gaps between interactions in the dataset and specifically between the target items and the previous one. Here are examples for the last and first targets. Across datasets, the first post-cutoff item demonstrates much longer time intervals, which could be attributed to a session-based nature of user activity. It could also be shown on the plot. The first target is skewed compared to the others, and we recommend avoiding it as a test target. Now let's move to the assessment of the evaluation results consistency. We know that absolute metric values vary across splits, so the ranking of models matters most. We trained multiple configurations of sequential models and analyzed Kendall and Spearman correlations between metrics for different splitting strategies to identify splits which are better aligned with successive evaluation scheme. We found that the random and last item targets show the highest correlations, whereas all and first item targets perform the worst, which we attribute to the task mismatch and temporal skew. The obtained results remains consistent across different k values. And the last question is, does these correlations affect the top-ranked models? And the answer is yes. Ranking for those models changed for different splits, which could affect the real deployment decisions. For example, here for the Digenetica dataset, the BERT4rec model could be the best performing model or drops to the third place under the some splitting targets. Overall, we observed that for the last random and successive targets, ranking remains relatively stable and becomes totally different for the first and all items targets. So the key takeaways are: leave-and-out split is easy to use and popular, but it demonstrates lower alignment with the real-world evaluation scenarios. We suggest further adoption of a global temporal split tailored for the next item prediction task for the evaluation of sequential recommender systems. This split is closer to reality, but it requires a proper test period and test target selection. We show that the all and first targets are less preferable due to the task mismatch and temporal skew. We suggest using the successive evaluation or last or random targets as proxies. That's it. Thank you for your attention.
You highlight how different splitting strategies can lead to very different evaluation outcomes. Doesn't that imply that the real challenge isn't choosing the right split, but that offline evaluation itself may be fundamentally flawed for sequential recommenders? How do you see offline splits even truly matching the dynamics of online deployment?
Actually, it's an interesting question. And yes, we are aware that online and offline performance could be not that aligned. And we tried our best and we proposed that successive evaluation be showed to you. And I hope that community will continue our work and propose something else which is more tailored. But for now, actually, I don't know what to do.
Yeah, we actually show 5 splits, some of them totally incorrect and totally unsimilar to the online setting, and some of them more likely to the online setting. So you can choose better splits instead of worse one.
So thank you for a nice talk. This problem of pervasive, unrealistic offline evaluation methodologies has been well known for years. Can you comment on why you think this is? How can we move towards more realistic settings being adopted? The problem is that basically, if you don't use this global time splitting, any kind of offline evaluation is flawed. Okay? So the author of the question, Olivier, is asking for a suggestion on how we can solve it for basically for academia, but also for industry.
So we should basically adapt some strategies that we propose, maybe, and read the papers, check the top papers, fundamental works, and see that they are moving towards using the global temporal split with next item prediction and use splits like them.